Hello everyone, welcome back to the lecture, the second part of the 23rd lecture in the series Mathematical Methods for Economics. In the first part we were talking about these properties of continuity and differentiability and how they're related to each other, and we showed that while every differentiable function is necessarily continuous, every continuous function is not differentiable. So let us we have to complete this proof. So I was trying to show that if a function is continuous at a point x equal to a, it need not be differentiable. So to show this, to prove this, we are taking this example here, f of x equal to mod x minus 1 plus 3. So here we have that if I want to explore if the function is differentiable at x equal to 1, first of all, we can take a visual look at this particular graph. This is a V-shaped graph, and here again you can see that you have this kink or a corner which I talked about in the first part of the lecture. So the graph here again does not have a unique tangent. The function is continuous because there are no breaks in the graph, but at x equal to 1 the function is not differentiable. Let's mathematically prove this. So if you notice here, the function mod x minus 1 plus 3 can be written as x plus 2, because if x is greater than or equal to 1, mod x minus 1 will be x minus 1 itself. So x minus 1 plus 3 is x plus 2. But if x is less than 1, then x minus 1 mod would be 1 minus x, and that is going to give you 1 plus 3, which is 4 minus x. We're now in a position to calculate the left side and the right side derivatives. The left side derivative would be the limit of f of x minus f of a divided by x minus a as x tends to 1 from the left of 1, okay, from values less than 1. So you can see here for that the relevant part of the function is 4 minus x. So that would amount to taking the limit of 4 minus x minus f of a, which is 3 because f of 1 is 3, divided by x minus 1. A here is 1. So that then gives me 1 minus x divided by x minus 1, and once I apply the limit, I get minus 1 as a left side derivative. On the other hand, if I calculate the right side derivative, the limit of f of x minus f of a divided by x minus a as x approaches 1 from the right will be the limit of x plus 2 minus 3, because when we approach 1 from the right, this is the relevant part of the function that will come in. So x plus 2 minus 3 divided by x minus 1, and that if you just simplify, that is equal to 1. So clearly you can see that the left side derivative is not equal to the right hand side derivative. The left side derivative is minus 1, the right side is 1, and clearly in this case the function is not differentiable. Okay, so next we'll move to some simple rules. I'm going to prove some very simple rules for differentiation, and these are actually really important because you are able to forego that the limit definition and just straight away apply the results which we're going to prove now. The first rule here is that if you have a function which is nothing but a constant, so you can see you just have a horizontal line here shown in red, that is our function. It is horizontal at capital A. Then the derivative of this function f prime of x is 0 everywhere. And why is that? Because this is a horizontal line. The tangent to this line everywhere is going to be flat. It's going to have a slope of 0. So intuitively, if you look at the result geometrically, actually, the slope, because the derivative is nothing but the slope of the tangent to the curve at a point, the slope of the tangent here everywhere is 0. We can also prove this result mathematically because f prime of x is the limit of f of x plus h minus f of x divided by h, as h tends to 0 by definition, because it's the function is a constant everywhere. So whether I take x plus h or x, the value of the function f of x plus h, f of x, whichever value you take, that is just going to be a itself. And here you can see that the limit would just be equal to 0. So that is the derivative f prime of x. Suppose we now have, this is rule number 2, let's define a function g of x which is equal to a plus f of x. So let's suppose we have a differentiable function f of x, small f of x, and a plus f of x, then visually you can see from the graph here that a plus f of x is simply just a parallel upward shift. If I take a as positive, it's just a simple parallel upward shift of this graph in blue upwards. It will shift upwards parallelly by a units to this to give you this new curve which is representative of g of x, that is a plus f of x. So what we are trying to say here is the result says that the derivative g prime of x is exactly going to be equal to f prime of x, which is to say that this additive constant a is going to disappear when you differentiate. And why is that? Because at any point, because you're just taking the new curve in terms of a parallel upward shift, the slope of the tangent to the curve at a given point will not change. So if you notice here at this particular point, I think the x equal to a marker has vanished for some reason. So anyway, so if we take this point at x equal to a, the slope of the tangent to the curve at x x equal to a for this function f of x is the same as the slope of the tangent to the curve here for a plus f of x at the same point. Right, because it's a parallel upward shift. So the derivative will not change, and that is why you get the same result. Again, we can prove it mathematically. G prime of x is the limit of g of x plus h minus g of x divided by h as h tends to 0. Just put in the values a plus f of x plus h, which is what g of x plus h is going to be. G of x is going to be a plus f of x. So once you do the algebra, the a's cancel out, and you can see that you're left with nothing but the formula for f prime of x, which is a limit of f of x plus h minus f of x divided by h as h tends to 0. So clearly you can see that the additive constant has no role to play. The derivative of the new function, the additive constant just disappears with differentiation, and the derivative of g, the function g, is the same as the derivative of the function f. Now suppose we, instead of having an additive constant, we have a multiplicative constant. Here you see, if you look at the results here, that if we define the function g of x as capital A times f of x, where we assume that f of x is differentiable, the derivative of g prime of x is equal to capital A times f prime of x. So the multiplicative constant stays when we differentiate here. And you can see here mathematically also why that happens. So g prime of x is a limit of g of x plus h minus g of x divided by h as h tends to 0. G of x plus h is a times f of x plus h, and g of x is a times f of x. So all we can do here is we can take a common, right, in this step, and because the limit is over h, so capital A will not be affected by this limit operator, so a can be brought out of the limit, and we are left with a times f prime of x. Okay. The next rule, rule number 4, that is a very important rule. It is called the power rule. So here we have that if a function f of x is given by x to the power n, where n is any arbitrary constant, then the derivative of the function of x is given by n times x to the power n minus 1. Okay. While this result holds for any n belonging to the real space, so n is an arbitrary constant, it could be a rational number or an irrational number. The proof that I'm going to show here right now is where n is a natural number, because right now we're not in a position to handle the other cases, but very soon we will be coming back to this proof to complete it. So as long as n is a natural number, let's see how the proof goes. So f prime of x will be the limit as h tends to 0 of f of x plus h minus f of x divided by h. F of x plus h is x plus h to the power n minus f of x, which is x to the power n, and this is divided by h. Further on, I can write this in this fashion, and I can use a binomial formula to open up the brackets x plus h to the power n, which will give me x to the power n plus nc1 x to the power n minus 1 times h plus the terms containing the higher powers of h, you can see here, and then subtract off that last term x to the power n. So clearly you can see the x to the power n terms will get cancelled. And now in this expression here, I have all terms containing an h, so I can take h common, and you can see here the h in the numerator and denominator will get cancelled. So the brackets, I'm left with nc1, which is nothing but n, x to the power n minus 1 plus these terms which contain higher powers of h. But once I apply the limit as h tends to 0, all these terms in the brackets except for the first term will disappear, and you'll be left with nc1 x to the power n minus 1, which is the result that we want for the power rule, that if a function is x to the power n, the derivative of the function is n times x to the power n minus 1. The next rule is also important, and at the same time it's very simple. If I have two functions, small f of x and g of x, which are differentiable, and I define capital F of x as f of x plus minus g of x, then the derivative of the sum or difference is the sum or difference of the derivative. So f prime of x is small f prime of x plus minus g prime of x, and this I'll leave this to you as an exercise. The steps are very simple. You can look at the slide here, they're all here in front of you, and you can walk yourself through the steps. I'll move to a very important rule, which is the product rule for differentiation, and this is saying that if a function capital F of x is defined as a product of two differentiable functions f of x times g of x, small f of x times g of x, then the derivative of the function capital F of x is given by the derivative of the first function times the second function plus the derivative of the second function times the first function. So this is known as a product rule, and let's quickly derive it. So f prime of x is the limit of capital F of x plus h minus capital F of x divided by h, and once you substitute capital F of x plus h, that is small f of x plus h times g of x plus h minus f of x times g of x divided by h. Now, because just to cheat a little bit, because I ultimately want small f prime of x in the result, so what I'm going to do is I'm going to manipulate this expression here in the numerator, and I'm going to subtract and add f of x times g of x plus h in the numerator, which is not going to change anything, but that will help me get my result. And then you apply the limit as h tends to 0 after you divided this expression by h. So if you notice here, once I do this, I can take from the first and the third terms in the numerator, I can take g of x plus h common. That will give me f of x plus h minus f of x, okay, plus, and then from the second and the fourth terms, I can take f of x common, and then I can write this as f of x times g of x plus h minus g of x. The whole thing divided by h, and then you take the limit as h tends to 0. This would then give me, if I just separate out the two terms, so g of x plus h times f of x plus h minus f of x divided by h, applying the limit to both of these parts in the fraction separately. So the limit as h tends to 0 of this expression plus the limit as h tends to 0 of this expression, f of x times g of x plus h minus g of x divided by h. And now you can see that this expression here is nothing but the derivative of f with respect to x, right? So that gives me g, and once you put h equal to 0, you'll get g of x times f prime of x plus the second term will give me f of x, right, times g prime of x. This expression here, once you apply the limit, that will give you g prime of x, and that is exactly the result that we have a product rule, that the derivative is the derivative of the first function times the second function plus the derivative of the second function times the first function. A lot of the books also write this as the first function times the derivative of the second function plus the second function times the derivative of the first function. Whichever way you're comfortable remembering this rule, the point is you must remember it. And finally, we have the quotient rule, where if we define capital F of x as the function small f of x divided by g of x, with g of x not being equal to 0, the derivative of this function capital F of x is given by the denominator g of x times the derivative of the numerator, which is small f of f prime of x, minus the numerator times the derivative of the denominator divided by the denominator squared. This is a very important formula again, and we'll be practicing problems with all these rules in the next video. But for the time being, let's just prove this quotient rule, because capital F of x is small f of x divided by g of x, and because we've already proven the product rule, let's make use of something we've already proven. See, a small f of x I can write as capital F of x times g of x. Okay, so applying the product rule, my f prime of x becomes capital F prime of x, the derivative of the first function capital F prime of x times the second function g of x, plus the derivative of the g function times the first function, which is capital F of x, right? Now, because ultimately I'm interested in calculating capital F prime of x, I can just move terms around and solve for capital F prime of x to get small f prime of x. I keep this term as it is and take this term to the left, which is g prime of x times capital F of x, divide the whole thing by g of x. And because capital F of x is small f of x divided by g of x, I substitute that in here, take the LCM, and what will you get? That's exactly the result that we want. Once I cross multiply, I get g of x times f prime of x, right? The denominator times the derivative of the numerator minus g prime of x times f of x. So that is the numerator times the derivative of the denominator divided by the denominator squared. So these are the 7 key rules, the 7 key formulas that you must be acquainted with, and it would be a good idea if you can go through all of these proofs once, because from what I know, many of you don't do these proofs in school, but it's always a good idea to know what the proofs look like if you're using these rules. So that is as far as these rules are concerned. Now, before we finish, let me just end with a concept. See, we have introduced the concept of average rate of change. We've talked about instantaneous rate of change, which is f prime at a. There is yet another rate of change, which is actually also very relevant for economists. And this is a calculation we use all the time. So this is something that you would like to know. So we are introducing here f prime at a as representative of the instantaneous rate of change of the function at a. And we can also bring in what is known as now the proportional rate of change, which is also called the relative rate of change of the function at a. And that we are defining as f prime at a divided by f of a. This is expressed as a percentage. Now, very often the variables that we deal with in economics, these are functions of time. So, if y is a function of time, okay, then the proportional rate of change is equal to, it's given by f prime of t divided by f of t. The same formula that you have here, except that now I'm just generalizing it to include the independent variable, which here is time. And because, as I told you in the beginning of the lecture, this notation that we use when we take the derivative with respect to time, we also use y with a dot over it. That represents dy by dt or f prime of t. So we can also write the proportional rate of change as y dot divided by y. And some people also write it as, so this proportional rate of change can be written as 1 by y dy by dt. So these are different ways in which you can write the expression for the proportional rate of change. We'll be looking at a couple of examples where we'll be using the proportional rate of change, the quotient rule, or the product rule, all of these simultaneously, so that you get your practice going for these concepts. But just before I wind up, just wanted to make one last point. which is that these proportional rate of change is something which you're using all the time, a lot of the time in economics in your calculations. So if we think of a lot of the the quantities that we come across in economics, first of all, note here, let me just back up. Here, the proportional rate of change requires you to calculate a derivative. But remember that you may not have a function which is nicely differentiable, and for example, in economics, you are dealing with quantities like talking of national income, or let's say the population of a country, or the price or demand, which you might not be measuring continuously, but you would be taking you would be getting the numbers at certain intervals of time, let's say over a few days or weeks, maybe quarterly or yearly. So the data that you would not would be you basically would be dealing with discrete variables here. So in that kind of a situation, when let's say I want to talk of the rate of growth, if you have done your first level macroeconomics, let's say you want to calculate the rate of growth in income, then you would take a discrete change. Let's say I want to know what is the rate of growth of income when you move from time period T1 to T2. That would you will take the final value minus the initial value divided by the initial value, right? So here you can actually take this as a discrete analog of this formula, because if I look at this formula in a discrete sense where you can't differentiate, but in a discrete sense, so that would be f of T2 minus f of T1 divided by T2 minus T1, because that will be your average rate of change, and that you divide by f of T1. Right? Now, T2 minus T1, if you're talking of numbers from one year to another or one period to another, T2 minus T1 you can take here as 1. So that percentage rate of change that you calculate, that here is basically reflecting your proportional rate of change in a sense. So with that, we conclude the second part of the 23rd lecture. That's all we had time for today. Thank you so much.